unless you have any question, we will proceed with the first talk. Okay, so it is my pleasure to introduce the first speaker of this morning session. It's Professor Peter Koepke, who will talk about 100 years of modern set theory, Felix Hausdorff foundations of set theory.
Yeah, good morning everybody. Thank you very much to the program committee for inviting me, and also thank you for the organizers of all these events to organize them. I know how hard this work is, and congratulations that you were so successful in your application. It's very nice to see so many faces, so many known faces around me, and this should help me in giving a talk which is quite unusual for me. This is not a technical talk, no blackboard, even the slides are of a different character, and I'll mainly read from my laptop. So this is very new, but with the help of everybody in the room, it should be all right. So I want to talk about 100 years of modern set theory, Felix Hausdorff's foundations of set theory. This is based on the book Foundations of Set Theory, Grundzüge der Mengenlehre in German, by Felix Hausdorff. I want to place the book in the context of historical developments of set theory, and alongside give a little information on Hausdorff's work and life. My thesis will be that the book very influentially marks the transition from the initial phase of set theory, in which Cantor and his followers were trying to grasp mathematical notions of set and infinite, into a mature and fruitful mathematical discipline. This picture shows Felix Hausdorff in his study in his house in Bonn, probably taken in the 1920s. I first have to present Grundzüge to you in some detail. This also is necessary due to the fact that Grundzüge has so far not been translated into English. There is a new printing of the book in the context of the so-called Hausdorff edition of collected works, but that has all been and mostly done in German, and also the commentaries are in German. So let me give a short presentation of Grundzüge. Grundzüge was published by Hausdorff in the spring of 1914, 101 years ago, when he was a full professor of mathematics at the provincial town and University of Greifswald in the north of Germany. Let me recall a few biographical facts about Hausdorff. He was born in the city of Wrocław, now Poland, and at the time part of Germany. His family moved to Leipzig, and that was the place where he started his academic career, promotion, PhD that is, and habilitation in the field of applied mathematics and astronomy. And then he did a lot of things after his habilitation, teaching a lot of different areas of mathematics before he became a professor at the University of Bonn. Then he became a few years later a full professor at Greifswald, where the book was published, and in 1921 he returned to Bonn. In 1942, due to the persecution of Jews, he, his wife, and his sister-in-law committed joint suicide. Hausdorff met Georg Cantor, the founder of set theory, probably in 1897 or a little later. He was immediately attracted to Cantor's set theory and started to work on it. He begins Grundzüge with a very honorable dedication to Cantor, whom he calls the creator of set theory, Schöpfer der Mengenlehre. Cantor, on the other hand, inspired and supported Hausdorff's work and career. He especially was fond of Hausdorff's work on cardinal arithmetic and ordered sets. Walter Burkhardt, who is the authoritative biographer of both Cantor and Hausdorff, and who is in charge of the Hausdorff edition at Bonn, describes Hausdorff as the mathematical successor of Cantor. For Grundzüge, Hausdorff chooses the style of textbook, directed towards students in their middle semesters, he says, but also towards colleagues. Given the unstable state of set theory before, we think of Cantor's difficulties in defining the notion of set, Russell's contradiction in the Frege class system or logic, the axiom of choice situation, Zermelo's axiomatics, which contain the vague, very vague notion of definite notion. This move turns out to be very smart indeed. It allows him to choose his own style. He is not, he doesn't have to follow any predecessors there. And what he stresses emphatically in his book is precision. He stresses complete gap-free deductions, and this can implicitly also be understood as a criticism against certain prior set theoretic work, even prior set theoretic work of Cantor, because he says we have excluded material that appears only trustworthy by personal credit, and we know that Cantor did a lot of conjectures in his publications, hoping that he would soon be able to prove the continuum hypothesis, and Hausdorff was quite right in being careful about such material. His aims, according to the foreword, are to systematize and organize existing set theoretical knowledge and to contribute, as he modestly says, some new aspects. Actually, some of Hausdorff's contributions have played tremendous roles in the further development even of mathematics as a whole. For this, let me just mention his axioms for topology. The textbook format gives Hausdorff a lot of freedom in presenting especially the foundations of the subject. The very first section of the text is called Der Mengenbegriff, the notion of set, and it is a two-page summary which sets the mathematical stage for the further development and which elegantly circumvents all previous foundational scruples. Hausdorff, in the interest of the set theoretic beginner, assumes the naive standpoint. This reminds us already of Halmosch's naive set theory, where sets are simply well-behaved mathematical objects, just like numbers or geometrical figures. So he says, since these, and he is thinking there of Zermelo's axiomatic approaches, exceedingly subtle examinations cannot be considered complete yet, and since the introduction into set theory of the beginner along these lines would be connected with big difficulties, we will admit the naive notion of set, but observe the restrictions which cut off the way to that paradox, meaning the Russell contradiction. So this allows him, without being clear on what the axioms are, what the foundations are, to just steer the readers through the field and at the same time work very formally and very correctly. Hausdorff was optimally informed about that paradox or the contradiction. Russell had published it in his Principles of Mathematics in 1903. not to be mixed up with the later Principia Mathematica. And Hausdorff had written a long and very scathing review of it, alas, published in some philosophical journal. But he was really upset about how could one, after discovering a contradiction, happily continue to develop that theory as a foundation of mathematics. So how does Hausdorff set up his set theory? What is a set? Let's first look at Cantor's classical definition. By a set, we understand any collection into a whole M of definite and separate objects, little m, of our intuition or our thought. These objects are called the elements of M. This is problematic because you somehow define one thing through the other. You want to define what a set is, and you go back to the notion of collection, and then you would have to ask what is a collection, and so on. There were other problematic approaches to sets through the years. So Russell, in his principle, discusses at length the notion of a class, and for him, because he is on the standpoint of set is equal to class at that time, but he doesn't give a clear definition or notion of set. Others, like Arthur Schönflies, who wrote a couple of reports on set theory, preferred not to consider arbitrary sets and only took point sets, sets of real numbers or similar, for intuitively granted. Consequently, those authors only considered ordinals and cardinals as far as they were needed in analysis, let's say up to Aleph 1 or Aleph 2, and because they also suppose that Cantor's continuum hypothesis is probably true, and so this was a very restricted view of uncountable combinatorics. Now Zermelo comes in, and he takes the Hilbertian axiomatic approach, avoiding the question of what the true nature of sets is. Zermelo says set theory deals with a domain B of objects that we will simply denote as things, among which the sets form a part. Yeah, so we have to think of things, and some of them are collected into sets, and then these should again be things. So things is the overarching notion or class, and within we have class, we have sets. And this is then regulated by the axioms that Zermelo introduced. Now Hausdorff combines both ways, the Cantorian tradition and Hilbert's formalism, and he starts his text with a very clear and simple statement. He just says a set is a collection of things into a whole, i.e. into a new thing. So, okay, he has the word collection around, but this collection is more seen as a technical collection, and we will just see in the future what collections we make. That's the naive approach here. And it's not so that we have to clarify first what a collection is. Theoretically, these things have to be taken completely formal and abstract, and you could say they are something like variables of a formal theory. Properties between things, relations between things, are introduced, well, for Zermelo with the axioms, or for Hausdorff along the course of the book. So Hausdorff says pure set theory completely abstracts from the nature of these elements, And then to aid the reader, and probably also to aid himself and every mathematician, yet we recommend to the reader to visualize them, if possible, as mathematical objects, namely points, figures, numbers, functions. So these are the things, and then some of them are taken together into sets. Now, with this partially formal approach, but guided by mathematical intuitions and applications, Hausdorff sets out to present a systematic and sophisticated set theory. Some foundational questions are already dispatched on page 1 of the book. And of course, this is now his freedom, that as a teacher to students, he can just state certain facts that he likes, and we have to follow them. So he says, the set of natural numbers, the set of points in space, are the immediate examples of infinite sets. So there we are. This is already first page of the introduction, and no question about that. We have natural numbers. We are not under the pressure, as we as ZFC set theorists might feel, to create these objects and domains out of the set material. Yeah, it's rather that we are working from certain atoms, things that are already there, and then set theory is done above or with these objects. So in the book, and here are the titles of the chapters, Hausdorff studies unions, intersections, first of arbitrary sets, and then things get a bit more specific. He is looking at cardinal numbers, at ordinal numbers. His sets are getting structure as linearly ordered and well-ordered sets. They get also other structure as point sets. He introduces topological spaces and is interested in subsets of those spaces. And this even specializes down to Euclidean plane or Euclidean space. And then he is also looking into a bit of real function theory and measure theory. There is a general tendency in the book to go from the general to the more specialized. So what I want to do to give you a flavor of this book is to discuss some passages, going from the easy to the more complicated. So let's look at this. He says a system of things, A1, A2, where every natural number corresponds to a thing is called a sequence. So he introduces words to you. The attentive student learns these words and repeats these words. So there are some words which are not really formally defined, but he appeals to your general knowledge, and also you're getting accustomed to them. But he is aware that, for example, systems such as sequence or so can be captured purely set theoretically if you wish. So he says, we can also see it like that. A sequence is an assignment of elements of a set to the natural numbers. Yeah? So he thinks these are all contained in some set, elements of a set, and the assignment is to the natural numbers which serve as indices here. A function defined in the set of natural numbers. But then he goes further, explaining the possibility of set theoretic formalization of this. He, in another place, says, consider a set P of such pairs, that is pairs which satisfy a certain functionality, and say that thus a unique function of A is defined in capital A. Yeah, so a function of A, this should now be the argument, is defined lying in some domain, lying in some argument set capital A. Which thing? Yeah. Hausdorff even has an ordered pair, if we want it, at his disposal. So he says, by the way, incidentally, the notion of ordered pair can be reduced to the notion of set if one so wishes. And he suggests this pair, and this is a perfect pair. Of course, it needs still these constants 1 and 2 that you have around as your atoms. And then if you do a few case distinctions, you realize that this has the axiomatic properties that we want from an ordered pair. This is quite typical for Hausdorff's style. There are mathematically important notions, and it is fruitful to use them in set theory. That set theory is, in principle, able to model those notions autonomously is taken as an interesting coincidence, incidentally, and his advice is to the reader not to bother too much about such foundational particulars. Note that there is also some foundational aspect involved in identifying Zuordnung, assignment, with a set, since from the ZFC standpoint, this seems to involve, however you formulate it, the replacement axiom or replacement schema. So alongside, he is sort of, without any reader noticing, introduces axioms, and you can argue that he even introduces the replacement axiom in his 1914 paper, although replacement was not yet there at the time. Now, this little excursion on sequences is part of Hausdorff's consideration of systems of sets closed under countable unions or intersections. So he uses it to show that for a given system M of sets, there is a smallest sigma system, meaning closed under countable unions, respectively delta system, which contains M. And we call it M sigma, the smallest thing, or M delta. So we are immediately in notions that are still being used. So if in some topological space we start with the closed sets, the sets Fermé, or we start with the open sets, the Gebiete, then we can from them form these collections F sigma, G delta, and so on, and we get into the Borel sets, which are also a topic of Hausdorff's book. So this is an example that notations that were introduced by Hausdorff in his book have become part of common mathematical language since. And probably many people even wouldn't know where these notions come from. Now let's make a little jump. Let's jump to cardinal numbers and cardinality. Hausdorff treats cardinal numbers and cardinality in the 3rd chapter. These notions, obviously central to infinitary set theory, posed at the same time a serious foundational problem. What is a cardinal? Cantor suggests that a cardinal of a set is formed by abstracting from the individuality of its single elements. So here's a set with the elements, but then you replace every set by the same marker, and you obtain something like a multiset of that marker out of a given set, and that looked for Cantor like the cardinality of the set. Russell takes the equivalence class under bijection. So Russell's 1 is the class of all one-element sets. But that gives you, of course, a proper class, and that reminds of the proper classes that you have in Russell's antinomy. Now Hausdorff takes an elegant formal turn here. Oh, it's already up. Yeah, we shall simply take the formal standpoint and say we assign to a system of sets, this is German, a system of things, German A or whatever you call it, in a way that exactly equivalent sets correspond to the same such thing. These new things we call cardinal numbers or cardinalities. Yeah, so we think of a function, a cardinality measuring function, which assigns to equal sized sets the same cardinal number, and these cardinal numbers, they are things. Yeah, this is the freedom of this approach, and you don't have to be more explicit about them. Of course, it's very nice that in nowadays set theory, such a cardinal function can be defined internally. Yeah, that we can, via ordinals and initial ordinals or something like that, or using Scott's trick, define cardinal numbers within sets. This is an advantage, but you could also see it just as a coincidence, and there is no a priori reason why it should be so. It could be that working in an enriched set theory with many things and having cardinal numbers as separate objects around is also a very good approach. And really, if we do set theory, we behave like that. We somehow think that the ordinals and the cardinals are types, and these types are somehow set apart from other sets that we are interested in, and so on. So this way of approach, this formal approach, is a very efficient one, and it circumvents the difficulties that others had with cardinal numbers.
Peter, could you clarify the chronology with Zermelo's treatment of the axiom of choice? I mean, what is the timing like when this book was written?
The book is from 1914. Zermelo's proof of the axiom of choice was in 1904, or published in 1904, right? Then there was discussion on the, let's say, justifiability of that proof, and a reaction to that was the 1908 paper of Zermelo, in which he proposed the Zermelo axioms of set theory. Yeah. But as far as I see it, Zermelo was really geared or looking at the proof of the axiom of, not the proof of the axiom, at the proof of the well-ordering theorem, and whether other parts of mathematics could be done in these axioms was not his primary concern. Infinite cardinalities were probably the main scientific motivation for Hausdorff to enter set theory. During his time as an applied mathematician, he had also published literary and philosophical works. His 1898 book, Das Chaos in kosmischer Auslese, translated, this is Chaos in Cosmic Selection, brackets, the world is a chaos out of which human minds can select various cosmoi, that is structured, nice worlds or images, and see this chaotic world, for example, as 3 or 4 dimensional. They can see it as parametrized by rational or real numbers and all these nice mathematical things. But this is a selection, Hausdorff would say, that the mind makes out of the chaos of the world. Okay, so this book, Das Chaos in kosmischer Auslese, aims at destroying metaphysical talk of a priori symmetry, harmony, etc. He is directed against all, one could say, philosophical metaphysics, and one of his arguments, or several of his arguments, use naive cardinality argumentation, For example, he wants to use that r to the n plus 1 is strictly greater than r to the n. Now, when he met Cantor, he learns about the equinumerosity of the reals and its finite powers, and so he has to go back to his book and he has to learn about cardinalities to get these things in order. One can find traces of Hausdorff's philosophical interests and mathematical applications to philosophy in the text of Grundzüge. So let me show you this. The Grundzüge der Mengenlehre was not easily received when it came out, because it came out at the outbreak of the First World War. So there was a long gap before many people realized the existence of the book. There is an interesting review which only came out after the First World War by Henry Bloomberg in the United States. It was in the Bulletin of the American Mathematical Society, and it's a long report, and Bloomberg seems to like the book so much that he writes the following passage. That the author enjoyed himself while at work may be seen from such passages as the following. From an alphabet, a finite set of letters, we may construct a countable assemblage of finite complexes, ordered sets of letters, that is words, among which, of course, meaningless words such as abracadabra occur. In addition to the letters, if in addition to the letters other elements are used, such as punctuation marks, type spacing, numerals, notes, he means musical notes, we see that the assemblage of all books, catalogues, symphonies and operas is also countable. On the other hand, if in the case of a finite number of symbols we restrict the complexes to a maximum number of elements, agreeing, for example, to rule out words of more than 100 letters and books of more than 1 million words, these assemblages become finite. And if we assume that with Giordano Bruno, an infinite number of heavenly bodies with speaking, writing, and musical inhabitants, it follows as a mathematical certainty that on an infinite number of these heavenly bodies there will be produced the same opera with the same libretto, the same names of the composer, the author of the text, the members of the orchestra, and the singers. So this is a pigeonhole argument with which Hausdorff wants to illustrate the magnitude of infinity over finiteness. But I think this is also somehow close to his heart, because it illustrates, or it can be interpreted from a few other perspectives. Hausdorff was a follower of, one should say, part of Nietzsche's philosophy, and he had himself written a book of aphorisms which was called Sant Ilario, Gedanken aus der Landschaft Zarathustras, Sant Ilario, thoughts from the landscape of Zarathustra, reminding us of Nietzsche. And Nietzsche had the idea of the eternal return, meaning that certain world constellations will recur infinitely often in the course of time. And Hausdorff's snippet here on symphonies and operas is based also on a pigeonhole principle, which could as well imply Nietzsche's eternal return. So this is, I think, an important thought to him, that this Nietzschean idea can be partially pursued with mathematical means, that cardinality gets into it. Maybe the old distinction between finite and infinite has to be made more subtle, and set theory is a means of providing such higher cardinalities. Another aspect concerning this bit here is that Hausdorff was a very literary man. Beside aphorisms, he wrote poems, essays, literary criticism, and even a comic theater play. His mathematical publications are full of very beautiful and elaborated language, as I have slightly indicated so far, and this may be one reason why Grundzüge have not so far been translated into English. There was in the Hausdorff edition, when it started in the early 90s, a discussion whether everything should be done in English, and I think it's a pity that it hasn't been done. But Brieskorn, the motor behind this edition, a topologist, he was very keen on Hausdorff's exact language. He wanted to present and preserve that, and I think that is the reason why the edition exists mainly in German. Only parts, commentaries written by non-Germans can be found in English in there. Then another aspect I would like to mention is that Hausdorff's deep and initial love was not mathematics or astronomy, but it really was music. He wanted to study and become a conductor or a composer. But his father, a successful businessman, only allowed him to study applied mathematics and astronomy. And indeed, in the research for the Hausdorff edition, a lot of effort was put into finding out whether some compositions of Hausdorff might be around somewhere. And they went to the Nietzsche archive and looked through Nachlasses, but alas, didn't find any Hausdorff music. Okay, how does the book go on? After the Grundzüge chapter on cardinalities, Hausdorff devotes 3 chapters to ordered and well-ordered sets, including ordinal numbers, of course. Most of the results were already presented in Hausdorff's earlier article, Grundzüge einer Theorie der geordneten Mengen, Foundations of a Theory of Ordered Sets, which was published in Mathematische Annalen in 1908, which is the same volume in which Zermelo published his axiomatization of set theory. There are indications that Hausdorff's research on ordered sets was motivated by the continuum problem. There are Aleph, that is continuum many, ordered types of countable linear orders, and there are Aleph 1, ordered types of countable well orders. If one could, for example, and I think this was an avenue that Hausdorff tried, classify countable linear orders by countable ordinals, let's say finitely many countable ordinals, this would prove the continuum hypothesis. But Hausdorff was very careful not to make any unjustified claims or conjectures about this. Hausdorff's work on orders has led to a host of important results and notions. He characterized density and completeness of orders versus gaps in linear orders, and these subjects are still actively studied presently. Hausdorff isolated in his studies the notions of co-initiality, and we know more about co-finality, which are so important in uncountable combinatorics. Co-finality was instrumental in Hausdorff's clarification of Koenig's false claim at the ICM, International Congress of Mathematics at Heidelberg, that the reals could not be well ordered. Yeah, there was quite some confusion when Koenig used something, one could say, like a version of the Hausdorff recursion principle in cardinal arithmetic, not distinguishing between successor and limit cardinals, and So then the reals could not be well ordered against Cantor's expectation that everything could be well ordered, and then the exact analysis of it, and Hausdorff had his notion of cofinality already at hand, showed that one really has to look into limits, successors, cofinalities, and so on. The consideration of saturated linear orders, where a lot of the gaps are filled, in higher cardinalities motivated Hausdorff to formulate first the generalized continuum hypothesis. So the generalized continuum hypothesis does not go back to Cantor. Cantor conjectured that 2 to the Aleph 1 is Aleph 2 in some place, but the generalization to all places in the cardinal hierarchy is due to Hausdorff. Because this comes up and because it's also nice and satisfying for set theorists, Henry Bloomberg, in the report that I quoted from, where we had this long translation of the Hausdorff piece, he said, if there are still mathematicians who hold the theory of aggregates under general suspicion and are reluctant to grant it full recognition as a rigorous mathematical discipline, they will find it hard to retain their doubts under fire of the logic of Hausdorff's treatise. It would be difficult to name a volume in any field of mathematics, even in the unclouded domain of number theory, that surpasses the Grundzüge in clearness and precision. But now I must mention, of course, the axioms for topological spaces, because this is, as I already mentioned, the most influential single contribution of the book. Hausdorff gives the axioms and then creates the field of general topology as a natural application of set theory to arbitrary topological spaces. And all the basic notions that we learn in our undergraduate studies are there: open, closed sets, compact, dense, connected sets, first and second countable spaces. And I think they are called first countable and second countable because Hausdorff in his book had numbered them 1 and 2, and these numbers are still being used. To be fair, in topology, so this is slightly different from Cantor's creation of set theory, most of these notions had existed before in some form and some degree of specialization, and people had already proved important results. But only the general notion of topological space created an appropriate framework for all of these previous attempts on topology. There's a lot more impressive material in Grundzüge, but in the interest of time, I've already written this here in my paper, but probably I have even to shorten more than I thought. I want to conclude the presentation mentioning 2 outstanding results from the appendix. One of the results is that Hausdorff proves the continuum hypothesis in form of the perfect subset property for G delta sigma delta sets. So he is going in the direction of Borel sets, and he can go 3 steps up and or how many steps you want to count here, and and get the perfect subset property there. He conjectures that this can be extended to all Borel sets, and indeed this happens in 1916 by himself and independently by Alexandrov in Russia. So Hausdorff is very much also a descriptive set theorist, and when the Grundzüge were republished in 1927, they came out, the second edition was really a new book. So he, for some external reasons, had to shorten it a lot, and then he exchanged a lot of the material and put in descriptive set theory and metric spaces instead of the general viewpoints of ordered sets or general topological spaces that he had in Grundzüge. And one may argue even that that second book of Hausdorff, second math book of Hausdorff, shifted the descriptive theory away from descriptive function theory, as it was for Borel, Baer, Lebesgue, and so, to descriptive set theory. So I think one can argue that there was a strong influence on the future of descriptive set theory through Hausdorff's second mathematical book. And then I just want to mention that in the appendix there's another very spectacular result, namely the Hausdorff paradox, which allows to decompose a sphere into three parts so that two of them really recompose as the whole sphere except countably many exceptional points. And this is the beginning of all these paradoxical decompositions, and also has to do a lot with measure theory.
Can you just remind us how many years before Banach and Tarski this was done?
Well, he had done it in 1914. Now, if you know when Banach Tarski have done it,
I think it was in the 20s, does anybody know?
yeah, it's around 1930, but I have no exact.
Really many years.
Sure, yeah. Okay. So, there were other books on set theory, books and reports before, starting from Cantor's papers, and then Schönflies wrote quite a lot of reports to the German Mathematical Society. Here are other authors. But all these books can be distinguished from Hausdorff's book in that they are in some way or other, and I said this before, restricted maybe to point sets, or they are restricted in their mathematical reach because they emphasize too much the foundational issues. Hausdorff was a book which could encompass all areas of mathematical set theory at the time into one frame. Pure infinite set theory, set theoretic topology, point spaces, metric spaces, measure theory. Each of these areas is comprehensively introduced in Grundzüge and enriched by new notions and results. After Grundzüge, all these sub-areas continue to grow, and it will not be possible again to write a Grundzüge-like textbook covering these sub-areas side by side. So in this sense, Hausdorff books is a singular event in the publication history in set theory. So why should we call Grundzüge modern? What is modern about it? Naively, we might call it modern because some topics are treated similar to how one would do it today. Yeah, we are modern, and everybody who is behaving similarly is also modern. One could even imagine to teach selected parts of set theory straight from the book, and indeed this has been done for many decades after the publication. But of course, in culture, science, there is a general notion of modernity, and let me just say after 1900, but of course it's much more elaborate. In mathematics, we think of modern algebra, the book by van der Waarden, and van der Waarden very much was influenced by Emil Noether, whom he would call very modern, and then he characterizes her mathematics as all properties of numbers, functions, and operations will only then become transparent, generalizable, and truly fruitful when they are separated from their particular objects and are expressed as general conceptual connections. This is a bit different from pure or naked formalism because what she wants is that these notions are not just, let's say, formally correct or consistent, but you want them to become transparent, generalizable, and fruitful for mathematics. And one has, of course, the example of the modern algebra here, but I would argue that in this sense also Grundzüge is a modern book. Hausdorff's naive approach takes sets and their elements as atomic, unstructured things. Deductions are solely based on explicitly stated properties of things, and these notions, Hausdorff's abstract notions, turn out to be mathematically very fruitful. Here is a slide which I could skip, but I don't want to. This is about Hausdorff's philosophical background. So what was his real thought about mathematics? I mean, he was not just a mathematical educator or writer, but he had his own idea on the foundations of mathematics, and this was a radical formalism. So he was taking Hilbert's formalism. Hilbert maybe had just used it as a device. Hausdorff took it as an ideology, and in his report or review of the principles of mathematics, he writes the following very strong words. Formalism, which dominates modern mathematics in an ever-growing determinateness and consciousness. Formalism, which originally only intends to clearly bring out the premises of each deduction and to avoid nebulous appeals to the seemingly self-evident, and which in its further development has led to the complete emancipation from intuition and other specific extra-logical sources of knowledge, and which in its present form also defines, and now it really becomes ideological, and Hausdorff defines a duty and a right of pure mathematics, the duty never to recur onto the accidental actual meaning of the objects and their relation, but to define and deduce from precisely given undefined notions and undeduced judgments everything else, and the right to give such a logically built system of things and relations every logically admissible interpretation. So this is from this Russell review, and Hausdorff is privately very determined on this standpoint. Yeah? Mathematics is a formal game, but it's a game carried out by intelligent people who derive interest and joy and satisfaction out of working in these formal systems. So he should have been a logician, but he was not. Yeah? He did put a lot of effort into the Russell Review, but he was in the end so frustrated by the experience that later on he completely ignored the development of logic. He has an extensive Nachlass, more than 20,000 pages of handwritten notes, but the name Gödel does not exist at all in this Nachlass. Okay, let's quickly and finally come back to Grundzüge. Although its impact was initially stopped by the outbreak of war, in the long run it was a crucial factor in the development of modern set theory as we know it. The European Set Theory Society did very well to identify roots of many of today's set theoretical research areas in Hausdorff's work and interests. And the Society did very well to name the medal to be presented at the conference after Felix Hausdorff, the successor of Georg Cantor. Since these conferences take place in odd years, my lecture could not be given 100 years after Hausdorff's Grundzüge, but 101 years thereafter. Thank you for your kind attention.
Any questions or comments? Just a small comment. I wonder why
Koepke's definition of pair is somehow universally accepted. I mean, it seems more economical. Hausdorff is more intuitive and symmetrical.
Yeah. Yeah.
So surely you want intrinsic things to be inside systems. You don't want 1 and 2 as external objects. Because then you can build systems with...
There are many different versions of the Hausdorff, yes.
but they
It's
always
not
have
canonical.
external
Yes.
tags, 1 and 2, or 0 and 1.
Yes. But there is, a pair has a first and a second component, so 1 and 2 is...
You have to build within an axiom, you need order pairs.
Yes, Andres?
Let me continue on the tangent that Martin asked about. Koepke was not just defining ordered pairs. His goal was to describe, in set theoretic terms of those days, what an ordering. I don't think he meant linear ordering is. And the idea was that you describe an ordering of a set as the collection of non-empty initial segments. And then his definition of ordered pair just falls out as a special case of two-element set.
Joel?
Yeah, I have a question. So you've argued that Hausdorff's text is sort of the advent of modern set theory, but in light of the fact that set theorists today are generally working in a formal system like CFC, and Zermelo's theory was available to Hausdorff, yet he didn't use it, doesn't this undermine your argument a little?
Well, perhaps we are not working in modern set theory, but in partially in postmodern set theory. This is perhaps one thing which I just want to put in the air. Yeah, I don't want to really discuss it. Well, in a sense, he was working in Zermelo set theory, but he preferred just to work in it and not to delve too much into, let's say, logical setup before starting it. Also, keeping in mind that Zermelo had these definite notions around. The axiom of subsets, Aussonderung, was only available if you were certain that you had a definite property with which to do Aussonderung. So there were still tricky questions about the Zermelo axioms if you wanted to use them, and especially you want to use them for such a broadly orientated presentation.
Yeah, Bob?
To respond to Joel's comment, I would say set theorists do not work in ZFC. Mathematicians work in ZFC. Logicians are the only mathematicians who do not work in ZFC, especially set theorists work in all sorts of extensions and restrictions of ZFC. We use these axioms as a tool to do, and these and related axiom systems as tools to do Hausdorffian sorts of explorations about what's there.
Adrian?
Is there any correspondence known between Hausdorff and Hardy? G.H. Hardy?
I don't think so.
Okay, so let's thank the speaker again.